the problem I will explain today is the inverse shape problem. Set suppose that you have an obstacle, let's call it as D, which has different material property from the background. At this moment, the governing equation is the conductivity equation, and it could be elastic wave equation or Helmholtz equation. So, but I will explain with the simplest model. So let's say D has conductivity constant K, and the background conductivity is 1. If you have nice result for this case, then this constant conductivity could be C2 function, and also the conductivity inside D could be against C2, but it should have some discontinuity. And then the question is, when you apply electromagnetic wave, in this case just harmonic function, then if you don't have this obstacle K, then the H stands for Laplace U is 0. But in the case you have an obstacle, then the solution to this equation, the Laplace U is 0 inside the obstacle and outside the obstacle, and has a transmission condition on boundary D, has now solution U. So without D, the solution is H, and with D, the perturbed solution is U. And then we measure far away from D, the U when S equal to R, and then how can we reconstruct the shape of D? And this, so this problem is also related with small anomaly detection inside a body. For example, you want to test whether you have breast cancer or not, and that cancer has small size, and then you measure U, which is the voltage potential, and H is the given harmonic solution, assuming that there is no cancer. But in the case we have small cancer inside omega, then H is perturbed, and we say the solution is U. And now you measure U on the boundary omega. And if you compare these two different cases, the first one, the given domain is bounded, but they include the small anomaly is small, and you measure U on the boundary omega. And in this case, your D is not small, it's side which is bigger than wavelength times half. So in this case, it is not small, but instead you measure it far away. So these cases are very similar. So if you understand one cases, and the other cases also can be solved. Oops. Doesn't go to the previous slide. And now, if you look at this asymptotic expansion, the U is the perturbed solution and H is the given harmonic function. And then the difference is the summation of derivative of fundamental solution to the Laplacian. So derivative of gamma times m alpha beta, we call it as generalized polarization tensor, and the derivative of applied harmonic function. So if you measure U, if you have far field measurement, then the m alpha beta can be obtained. Just let's assume, there is a simple way to get m alpha beta. So the information we get is this polarization tensor m alpha beta. Then to get the shape of D, now we should know what is the relation between m alpha beta and the shape of D. The m alpha beta is integral on the boundary D of y to the beta times the potential function phi alpha, and phi alpha is the solution to this boundary integral equation, lambda minus kd star inverse times normal derivative of x to the alpha. So you have this sub-index alpha from this x to the alpha, this multi-index. And kd star is boundary integral operator on D. So now the information you have this integral boundary of y beta times phi alpha on boundary D, and now our question is to get the shape of D from the information of m alpha beta. So in the first case, where the inclusion is small and you get measurement on boundary omega, it's very similar. From the boundary measurement, you get the polarization tensor m alpha beta, and again, you have the same question. From the m alpha beta, how can you get the shape of D? And this, the general polarization tensor has been used to detect the small inclusion case. So when you have m alpha beta, for alpha plus beta is 2, then it determines one ellipse, and for alpha plus beta is 3, then it determines the location. So you measure your own boundary omega, you measure the far field data. Then for alpha plus beta is 2, you have m11 and m12, m21, and m22. And then there is some symmetricity, so m21 is the same as m12. So in the case you have m alpha beta for alpha plus beta is 2, that means you have 3 numbers which can determine the shape of this small inclusion. Actually, it's known that for this 3 number, there is one ellipse. Because you should have the length of 2 axes and the angle from the x-axis. So yeah, there were works to get the character, shape, and the location from this first order generalized tensor, and then yeah. So my question is, what about in the case we have the higher order polarization tensor as well? Not just the m alpha beta for alpha plus beta is 2 or 3, but how about we have alpha plus beta up to capital N? So for more information, how can we have finer detail? And here I follow the optimization approach. since we know the ellipse shape, I start from this ellipse and then change little by little such that the Polarization tensor correspond to the actual one, and the one we reconstructed has the minimal distance. So after doing some stuff, iteratively I changed my initial guess to be closer to the actual one. So today I followed optimization approach. This is the simplest case. Let's say we want to have the 0 point for the function f of x, and it is differentiable. So f of x is similar to f x0 plus x minus x0 times f prime x0. Then our next updated solution should be x0 minus delta, and delta is f x0 divided by f prime x0. So you can see that in the optimization approach, we need derivative of an image function. So in our case, since we want to have the shape, the derivative we should get is in terms of the shape. So I will explain you how we can get the shape derivative of generalized Polarization tensor. So before that, I will explain the related work. In that case, so rather than get a small size inclusion, in a couple of papers I worked for detecting the shape of inclusion D, which has different material property from the background, and the size of inclusion is comparable to the background of data. In this case, how can we get the actual shape of D? Actual shape of D, in the case we know the initial guess. So here, suppose the true shape is the initial guess plus perturbation in the direction of normal derivative. So yeah, so D is assumed to is our initial guess is supposed to be close to the actual one, and our target shape is x plus epsilon h, which we should reconstruct times normal derivative. Then the question is how should we get this epsilon times h? And if you give a closer look to this the Darwin equation, then the important part happens on the boundary. So on the boundary you have transmission condition. For the Dirichlet one you have continuity, and for the Neumann normal derivative, the derivative from the exterior is interior conductivity times interior derivative. So now D is our initial guess, and the actual one is perturbed one from D. So the true transmission constant happens on boundary with epsilon. So one easy way to get the relation between U and the U epsilon is a linearization. So set U epsilon as U plus times U1 and just expand, just have Taylor series expansion and compare the transmission conditional boundary the epsilon. Then you just expand from exterior and interior and then match these two transmission conditions. Then you get this two Dirichlet condition and Neumann condition for the use of 1. To remind that use of 1 was the first order, the leading order perturbation. So U epsilon is U plus epsilon U1. So when you have measurement on boundary omega, since U corresponds to our initial guess, and U epsilon, we measure this functional boundary omega. So from the measurement you have boundary data for this epsilon times U1. And U1 satisfies these two transmission conditions. There are some related work about this. The Hitler-Rundle base proved the same formula, but in this case they used the variation of formula and changed the variable. But the result is the same. Your measurement U1 satisfies Laplace U1 is 0, interior and exterior of D, and satisfy the Dirichlet transmission condition and Neumann transmission condition, and boundary data is 0. Then how can you get the perturbation function epsilon times h from the measurement of V1? And you see that the k minus 1 is conductivity difference. U is from the initial guess, so we'll simulate the data. So, and h is the known function. That one we should reconstruct. So all the information except h is known, and since using this relation, what we can have is this formula. So you multiply V, and V satisfy the same equation as U with our initial guess. Then applying the divergence theorem, your boundary data, boundary measurement data on the U becomes integral boundary D. So this 1 minus k we know already, and then D is our initial guess, and h is the unknown function, and this bracket part is the function corresponds to our initial guess. So the left-hand side is from the measurement. The right-hand side, you have this unknown function h times the simulated data. So yeah, the right-hand side is integral h and phi on boundary D. So how can we get this h function? So I define this bracket part as phi of x, and then construct the set of these phi functions, and then let's say expand U as linear combination of these phi. So these phi functions are our basis function, and then if you expand all of function h as a linear combination of phi, then the data you have is inner product of phi times the unknown coefficient A, and then from this you get the coefficient. So let's say you have phi 1 to phi m, and from the boundary measurement, the inner product H with phi I is known. So I said H is AI phi I. If H is orthogonal to phi I, we cannot get that information because all the information we have is inner product with phi I. So the orthogonal component is invisible. So with what H is the linear combination of this basis function, and from the first information, I just take H with phi j, and is AI times phi I phi j. So to get this AI, I have this matrix times the coefficient is from the measurement. So final step, I solve this linear equation, and you get the coefficient A, and that coefficient gives you the perturbation function. And I do the similar thing for our initial problem. That was get the share of D from M alphabet. The first thing is to have the asymptotic polar. Before, the left-hand side was the boundary measurement there, but in this case, now the data we have is the polarization tensors. So rather than just compare one by one of each polarization tensor, we compare linear combination of it. So I take coefficient A and B such that this A times A upper times X upper becomes harmonic polynomial, and also summation of B better times X better is harmonic polynomial. Then the difference between this combination of polarization tensor corresponds to the actual one minus the one of our initial guess is again you apply some symptotic analysis and Divergent theorem. Then at the end you have this relation. The measurement data is the same as integral on boundary D. And is the function we construct times this bracket part which satisfy these equations. So that is only related with the initial guess, so we'll simulate that part. So again, I said H as the combination of this basis function. The information we have is H, inner product H and phi I. So I take inner product H and phi j, then final step is one matrix times coefficient is a measurement data. So this is the example when you have alpha plus beta 3. So for I said that if you have just leading order polarization tensor, then the shape you could get is an ellipse. These two correspond to this ellipse. And then for alpha plus beta 3, you have sinusoidal function, cosine 3 theta or sine 3 theta. In the case, our initial guess is the disk. So you have more possibility to have finer detail of D. So the leading order can just give you an ellipse shape, but now you have more possibility. And then now we'll explain you the reconstruction procedure. To remind that the data we have is U, and then H is applied function. So the data we have is U minus H, and then there's some method to get this M alpha beta. So let's assume you have M alpha beta up to M. And for M is 2 and M is 2, it has ellipse shape. And for some information of M equals 3, you can get the center mass. So the initial guess I get is an ellipse, and for each step, just increase K one by one. That first I use alpha plus factor up to K equal to 2, and then 3, and 4. So just increase one by one the information of the generalized polarization tensor, and I just follow the optimization approach. And here is one example. So yeah, this is the first initial guess. Initial guess from initial guess is an ellipse, and then just one by one just increase the information of polarization tensor, and then finally you have the similar shape. So here I use polarization tensor up to 6. And this one, this is the class of inclusions. Since our approach assumed that the D is simply connected, it couldn't be separated. But you will see that the boundary of the reconstructed one is well matched to the initial one. Yes. So maybe we can study more to separate these inclusions. That's my future plan. And all of what I explained is a general frequency case. See, I apply this harmonic equation, and the frequency is zero. And usually, when you reconstruct some obstacle, there are two different categories. The first one is the point-like obstacle, and the second case is extended target. And usually, if the target size is smaller than lambda half, or is bigger than lambda half, if it's smaller than lambda, we say it's point-like, and if bigger than that, then it's the extended type of target. But for the direct frequency case, it's not obvious. So here I said there's for the small inclusion case, from the boundary measurement, we just measure this. From the boundary measurement, we reconstruct the inclusions as an equivalent ellipse, and for the comparable size of inclusion, we also get the finer details. Then, how can we say when you have one D inside omega, and how can we say it's small or large enough? There is no actually method to separate these two cases. For non-zero frequencies, the lambda half is the borderline. If it's multiple of couple of lambda, then okay, it's extended target. It's smaller than lambda half. Okay, it's a point-like target. But for the zero frequency case, it's not yet verified. So how can we decide? Yeah, I mean, what included side is point-like or extended. So my another research topic is to understand the smallness. How small of D is that we can only get this elliptical shape. I mean, characterized as an elliptical ellipse, or if it's bigger than a certain if the size is bigger than which number, then we should consider it as extended target. That is my next research topic. Yeah. Thank you for your attention.